So good morning, and welcome to the Jule Gregory Charney lecture. My name is Paul Newman. I am the president-elect of Atmospheric Sciences. So I've been working with, or under Jim here. He's given me great instructions on how to do these introductions. He's also given me instructions on how to, learning to become the president. You know, handling his bags, polishing his shoes, and doing the Charney lecture introduction. Jule Charney was born January 1st here in San Francisco. So it's fitting that we are here today to have this lecture. He was born in January 1st, 1917. So he would have been 103 years old come January 1st. Well, it's really an honor to introduce what I would call one of Jim Anderson's stallions, Professor Neil Donahue, who is the Lord University Professor of Chemistry at Carnegie Mellon University, with appointments in both the science in chemistry and engineering, in chemical engineering, as well as engineering and public policy. Neil is the founding director of the Center for Atmospheric Physics and is now the director of the Steinbrenner Institute for Environmental Education and Research, which represents all of environmental scholarship at Carnegie Mellon. Neil has an undergraduate degree in physics from Brown University, but upon graduating he decided not to pursue the Higgs boson particle at CERN. He instead received a doctorate in meteorology at MIT on a Charney Fellowship, working with Professor Ron Prinn at MIT on the chemistry of the marine atmosphere. Before he went to Carnegie Mellon, he spent about a decade in Jim Anderson's lab. And in fact, there's a number of just astonishing scholars that have come out of Jim's lab over the years, doing field work and laboratory work. It's just amazing to see the number of people that have come out of that lab, and Neil is just another one of the, I joke because Jim actually used the words his stallions, but in fact they really are an amazing collection of scientists. Neil is a fellow of the AGU and also the American Association for Aerosol Research. And he received the Pittsburgh and Sellon Awards from the American Chemical Society, and has a huge number of publications, over 240 publications. So Neil is best known for his work developing the volatility basis set, which provides the framework for describing and understanding formation of organic aerosols. He's worked on atmospheric chemistry, from atmospheric chemistry all the way through policy. You know, ever since the Charney report was written in 1979. And as I've learned, you know, sort of the irony of where you start off in physics, looking at the Higgs boson, he's come around. He's doing particle research at CERN now, focused on chemistry and physics of formation of aerosols. So with that, why don't we give a big hand to Neil for his winning of the Charney lectureship for 2019. And you get a lovely certificate. Doesn't open? There we go. All right.
So it's all here. All right. I thought I was going to get introduced by an actor, but turned out he died. Thank you. That was very flattering, and it really is a tremendous honor to give this lecture on the 40th year of the Charney Report to the National Academies. And indeed, I entered MIT to study meteorology on a Charney report. I was actually going to do dimethyl sulfide, but as I was getting ready to prepare systems and do that measurement, all this work came out from this guy, Andre, and I figured that problem was done. So went on to work on organic compounds and have basically never looked back. The answer, by the way, to the title is nothing. They're not in there, right? So aerosols are not in the Charney report. And all of what I'm going to talk to you about today, really the credit goes to a group of really amazing doctoral students I've worked with, many in my group, so Meredith, Ching, Mingyi, Victoria shown here. My colleague now at Carnegie Mellon, Hamish Gordon, who was at Leeds originally, and I first met as a CERN postdoctoral fellow some years back, and then some data I'll show you from Martin Heinrizi, also from the CLOUD Consortium. CLOUD is an amazing consortium to work in, and I've benefited enormously from my association with that group. So for starters, the obligatory first topic is, of course, why my problem is the only problem. I hope you know that's a joke. But aerosols are extraordinarily important. Doug Warsnop likes to say, I mean, we've got these incredibly tiny concentrations of this stuff in the atmosphere, and yet they have outsized roles. We care about a microgram per cubic meter of aerosol in the atmosphere. A cubic meter of air weighs a kilogram, right? So that's a microgram per kilogram. That's a part per billion by mass. 10 times heavier than air on molecular weight. So that's a mole fraction of like 100 parts per trillion, 10 to the minus 10. It's an incredibly small number. It also means that a vapor pressure of 10 to the minus 10 atmospheres is going to matter. And if you've ever worked with vacuum pumps, that's a low, low pressure. So they're really amazing things, and they have outsized effects. And unlike what Ken Karslas said, if you saw the New Fellows program, I'm going to refer to New Fellows several times through this talk if you weren't in the session. I'll try to make that not too obscure. But aerosol climate effects are not the only thing we talk about. We care about particles because they kill. They're enormously consequential to human health. Something like 15% of all mortality on the planet is due to inhaling excess concentrations of fine particles. And this figure from a wonderful paper by Josh Apte shows the effect in terms of years lost in life. So that's dailies or delta life years on the y-axis, and then the cumulative distribution of population on the x-axis, up to 100% in different countries. So in the most polluted places, I'm just recruiting a student, trying to get him to join the group, who's from Egypt, a wonderful physics student at Carnegie Mellon, and he said, you should see Cairo. I said, I think India is pretty bad. And he said, you should see Cairo. And if you look there, Egypt is indeed pretty remarkable. Almost 2 years lives lost, 2 years of life lost in Egypt, a year and a half to a year in China and India. And the United States, even though our air pollution has improved enormously, I'm from Pittsburgh, I grew up in Pittsburgh, still about 100,000 deaths per year in the United States, more than murders and car crashes combined. So health effects are a huge deal. Of course, we do care about climate, and my Piers Forster moment, if you were in this morning's session, here's a probability distribution function. This is the warming due to carbon dioxide and other long-lived greenhouse gases, which you see along the top there in the colored stripe in watts per square meter. And a probability distribution showing our understanding of long-lived greenhouse gases is extremely robust. It's a nice, tight, normal distribution, around 3 and change, 3¼ watts per square meter of warming forcing, and we understand that. The problem is, or a big problem, is that the particles, of course, cause, we think, a cooling effect, but our uncertainty, especially of the change in particle concentrations from the pre-industrial to the present day, is very large. And if you saw Ken Karslas talk about our model, this is really the range of models and their representation of that cooling. So it's not really an uncertainty, but rather a distribution of the model predictions of cooling. And there's enormous variability. And that has 2 consequences. First of all, aerosols are indeed hiding a significant amount of the warming associated with long-lived greenhouse gases, but they only live for a week or so until it precipitates, until they rain out. So they're very short-term masking of the long-lived warming that's continuously replenished in the form of the pollution that kills people. But then if you add that to try to determine an uncertainty in our overall forcing, of course, in quadrature, our uncertainty is very large. So we don't know how large that masking, in fact, is. And that's the climate aerosol problem. So some of the work I will tell you about Hamish Gordon, working as a postdoc in Ken Carslaw's group, put some new particle formation that I will tell you about later into the GLOMAT model to simulate aerosol forcing. And this actually had to do with particle formation purely from organic compounds, alpha pinene specifically, that would have been occurring in the pre-industrial as well as the present day, and looked at the effect that had on the aerosol indirect effect and the aerosol cooling. And the net result was that that specific model run with the specific parameters and representation of the physics came with about a minus 0.6 of a watt of cooling. Okay, that's a number. And in fact, that number is quite consistent with the central estimate from the IPCC. So the arrow there shows you the estimate there. However, this is with some new physics, right? We had added in something new about pre-industrial aerosol forcing, which I'll get back to. If you take that out, so the nice thing, you put it in, take it out, see what the effect is, it says that the model run without that new physics would have been even colder, that there'd be even more cooling. And if you work through the complicated math there, there's an implication that the climate sensitivity that you would deduce based on matching the historical temperature and record would be a little bit lower. But both of those models are entirely within the range and near the central estimate, so it's not that big a deal. And if you talk to Andy Dessler about the perception of things actually getting wildly amplified when you get into the public policy space, you see that little difference between those two areas that is scientifically important. It's 0.2 of a watt. We care about that, right? That's not a trivial thing, but it's well within the central estimates. We published a couple of papers in Nature, in May of 2016. Hamish's paper in PNAS came out a little bit later. But in May of 2016, the two papers came out in Science, and this happened. So this is actually, if you read the quote, the Wall Street Journal picked this up immediately because the implication that there was a little bit less sensitivity to climate, and it pretty much immediately showed up in an energy speech by a candidate to be the President of the United States. That was a little bit sobering. We actually did have a discussion in Cloud. I could go back to my emails and pull them out if they get FOIA'd, that about the implications of this pure science paper in Nature and how that would be interpreted. And there was a relatively heated conversation within the consortium about that and about whether we should be paying attention to that. And I'll leave it there until you want to have a beer. So now let's put this in context. As I just said, from a wonderful paper by Ken, we care about the pre-industrial concentrations and formation mechanisms of fine particles because the indirect effect on cloud droplet number concentrations and the associated cloud albedo is very, very strongly nonlinear. It saturates. And so as you add emissions, as you increase the number of fine particles in a model, your sensitivity, the cloud albedo sensitivity, which is the derivative of this curve, reduces enormously. So depending on where you start on this curve, you're going to get a very different forcing as you make a change through anthropogenic emissions. And so that's one of the essential reasons we care about the pre-industrial concentration of number of fine particles in the atmosphere. And it's really, really hard to go back in time and count numbers of particles. We know how to do CO2, we know how to do other things, but counting numbers of particles is just a difficult job. And so we really do have to rely on our best understanding of physics and chemistry, and then our ability to model what was going on. And then we see some other very interesting things. This is a nice figure from a paper by Christina Williamson summarizing the findings of very high concentrations of particles in the tropical convective region from the ATOM measurements, showing a mechanism that would be very familiar to Andy from back in the days of CLAW. So this idea of the mechanism is not new. But that particle formation in the upper troposphere might be followed by subsidence and slow growth of particles that entrain back into the marine boundary layer and then serve as the source of condensation nuclei in a kind of a double loop associated with particle formation. And so we do indeed observe very high concentrations of particle, the community throughout the tropical convective region, as ATOM has shown, and as Andy has shown coming out of the Amazon. So okay, We care about particles, we care about numbers of cloud condensation nuclei, and without going into Kohler theory to any extent, to be a cloud condensation nucleus, you need enough moles of stuff in a particle to actually to help stabilize the formation of a water droplet. And so particles essentially have to be bigger than about 100 nanometers with some soluble stuff to be able to serve as a cloud condensation nucleus. And so that budget I was talking about of the number that we need to understand in the pre-industrial and the present day is the budget of particles, the number of particles that are bigger than some threshold size. And we're using 100 nanometers here as that threshold size. And this is from the work of Peter Adams' group at Carnegie Mellon, Dan Westerveld, a PhD student of Peter's, showing a global budget for CCN. In a model that represents, it has the Peters-Thomas algorithm that represents number and mass of fine particles with a high degree of precision and the best known science at that point in time. And the point here is in fluxes. So this is sort of a notional distribution on the y-axis, and the x-axis is something to do with size. And the enormous majority of CCN grew up. That's the basic point here. The growth into the CCN range completely dominates on a global average over primary direct emissions of particles that are actually big enough to act as cloud condensation nuclei. And then if we reveal the ultrafine mode here, we see a similar budget story. And it doesn't really matter if these are ultrafine emissions, in the lower left-hand corner is that arrow, or we're actually looking at nucleation. They all have to grow up. But most particles, most tiny particles formed in the atmosphere don't. It's a classic big fish eating little fish problem. Most of those little particles bump into larger particles and die. And only a few of them grow up to be CCN and have a climate effect. And so it's grow or die. We care about the growth rate of particles balanced off by the concentration of larger particles or the surface area that these smaller particles can run into. And the very large majority of the ultrafine particles don't make it, and they're in that X in the center of the ultrafine mode. And so our goal is to understand that, the nucleation rate, the growth rates, and the loss rates of the particles in the ultrafine mode before they make it to be cloud condensation nuclei. So what makes things grow? Condensation. It's really the only choice. I mean, some coagulation. The big ones can gobble up little particles and grow a little bit. But primarily, it's condensation of vapors from the gas phase, right? It's not not rocket science, as they say. So the condensation is going to be driven by some production of a compound in the gas phase. And I'm talking about aerosols and aerosols and aerosols. I'm about to pivot and reveal my true identity as a physical chemist who's interested in gas phase chemistry in the atmosphere. And I'm going to tell you that that is really important. So we have production on the left-hand side of something from the gas phase, and then I have a flux on the right-hand side, which is the concentration of that thing in the gas phase times the condensation sink, the total surface area, essentially, of those particles. And that's represented by that big green blob on the right-hand side. So running into stuff isn't really a choice. Yeah, you don't have a choice about, right? Anything in the gas phase, it's going to hit surface and condense. The condensation rate is really, really, really easy to calculate. And the molecules don't get to pick what they run into. You just hit something. And so really the interesting question isn't condensation, it's evaporation. What comes back off of the particles? What bounces off of them, maybe, in accommodation, or what re-evaporates from the particles. And that's driven by the Raoult law, essentially the mole fraction of things, or mass fraction of material in the particle, and that's that blue wedge. And then the actual vapor pressure, which are vapor saturation concentration, the C0 of this constituent I. So the activity, or fraction A, and the volatility, C0, drive the ability to come back off of those particles, and it's evaporation. And of course, the saturation concentration, Clausius-Clapeyron and all that, is a very, very strong function of temperature. So we care about temperature there. So it's evaporation, but it's also the difference in these two things we care about. So what we care about is saturation ratio, the ratio of the concentration in the gas phase to that saturation concentration there, and that gives us the net. So the net condensation to the particles is going to be the saturation ratio in the gas phase The activity, the relative humidity, is just the activity in the gas phase minus the activity, mole fraction, mass fraction in the condensed phase. The saturation ratio in the gas phase can get really, really, really big, even at steady state, if the saturation concentration is low enough. The activity in the particle is kind of stuck. It can't get bigger than 1, except in some fishy way that I'll talk about in a second. And so if I have something with a huge concentration in the gas phase, a huge saturation ratio, I basically don't care what that circle looks like. If I hit it, I'm done, and I'm condensing. It's only when they get similar to each other that I do. And this saturation ratio, this excess saturation, will head toward a steady state, and that steady state is going to be the ratio of the production to the loss term, the production divided by the condensation sink times the saturation concentration. Again, a strong function of temperature. And so that'll be the first part of the story that I'm talking about. Now, the one little trick is when the particles are very small, then I can essentially raise the effective activity calibrated to a flat surface through the Kelvin term, through the surface tension of the particles. And the only point here is that Kelvin term, we're used to it in Kohler theory, where we care about 10 micrometer nascent droplets or something. But you can express it as an exponential or decadal increase in effective activity, and the scale diameter is like 4 to 5 nanometers. So really small particles do care about curvature in my story. They get bigger than about 10 nanometers, and it's a very small effect for this story of condensation. So sub 10 nanometer particles have a difficult time growing, and they're especially interesting. Larger than that, it's a pretty straightforward calculation, really. So we care about this condensation sink for a lot of reasons. And this is a distribution of condensation sink, again from Peter Adams' work, at 2 sites in Europe. So the red is the Po Valley, the polluted Po Valley. And you see the condensation sink here in collisions per hour. And just a cumulative distribution here on the y-axis. And in the Po Valley, the sort of central number is maybe 100 collisions per hour. 10% of the time, it really is awful. And you see that distribution way up at the top, where gases are actually colliding with particles every second. But those are heavily, heavily polluted conditions. You go to Hutiala in the boreal forest in Finland, which is, of course, the only place in the world if you do this stuff, and you see that collisions with particles are maybe 10 in an hour. And so that's actually now getting to be fairly long lifetime in the gas phase before you hit a particle. If you go into the upper troposphere in the tropical convective region, presented a different way now from Christina's paper last month, we see the condensation sink on the y-axis against temperature on the x-axis, and the color bar is showing us the concentration of particles in that 3 to 7 nanometer range where it's really, really hard to grow, and those almost certainly nucleated. This kind of looks like China to me. But in the lower left there near Tibet, you see that there's high number concentrations when the condensation sink is really very small, so it takes 3 hours for vapors to run into particles there. And it's quite cold, 230 Kelvin or so. That's where you see lots and lots and lots of new particles. So that, again, is worth keeping in mind. Okay, particles are done. Not exactly, but now we'll go to the gas phase and that production side and gas phase chemistry. I'm going to slide this a little so I can see my time. Okay. So this is a little bit of a story of my favorite 2 reactions, and we'll start from the time I did spend evidently as a horse in Jim Anderson's group. We studied the reaction of OH plus NO2, largely because it was a source of uncertainty in stratospheric chemistry, to produce nitric acid. And so that's a couple of papers that we published in AGU journals back in the 90s, showing the pressure dependence and the temperature dependence of the reaction of the hydroxyl radical with NO2 to make nitric acid. And then also more recently, I've been very, very interested in the reactions of alpha pinene, and actually since my days as a doctoral student in Ron Prin's group, have been very interested in the chemistry of hydrocarbons in general in the atmosphere. And so this is work from my then doctoral student Albert Presto on the production of secondary organic aerosol. from the alpha pinene plus ozone reaction. And we've been looking at monoterpenes in various ways now for many, many, many years. And so those two reactions are the reactions we'll be looking at along with isoprenes. So monoterpenes or terpenoids and the OH plus NO2 reaction for the rest of the talk. These will actually all reduce to what I would call my favorite potential energy surface in the atmosphere. And I would argue the most important potential energy surface in the atmosphere, and that's the potential energy surface of either nitric acid or organonitrates with a peroxy radical and NO over on the left-hand side, kind of dropping down into some extraordinary, interesting peroxynitrates in the middle, nitrites in the middle that I won't talk about at all. And then on the upper right, we see RO plus NO2 or OH plus NO2, which can drop deeply into that well and make a nitrate. And the dynamics on that potential energy surface are outrageously interesting, but I'm not going to go there. But that is the most important potential energy surface in the atmosphere. And so indeed, with that sort of fundamental quantum chemistry perspective, we head back to CERN and look at particle physics and a very low energy, very high mass basis. And this is the cloud experiment at CERN, which I would argue is the cleanest 27 cubic meters on the planet at room pressure. It's extraordinarily clean. You can regulate the temperature from 230 to 330 Kelvin, do experiments from an incredibly well-defined initial condition. It's made of stainless steel, it's well stirred, and it's surrounded by several $1 million worth of mass spectrometers on the central plane there. We also have control over the production rate of ion pairs, by either allowing cosmic rays to simply illuminate the chamber, when the proton synchrotron beam is on, which it is not currently because it's being upgraded, we can bring in the proton synchrotron beam and a pion beam that mimics cosmic rays on the right-hand side there and generate ion pair formation rate up to conditions of the upper free troposphere. And then finally, we can turn on a high voltage electric clearing field to sweep any primary ions out before they have a chance to play and look at the neutral conditions that are going on. So we have very, very precise control over the role of charge in the formation and growth of fine particles here. And our role in this has been to look at mostly at particle composition using a technique that was developed by Joel Thornton, using an iodide chemical ionization mass spectrometer and collecting particles on a Teflon filter that we then thermally evaporate by passing preheated nitrogen, ultra-pure nitrogen over that filter to do temperature programmed desorption on the particles. We can also measure the gas phase using the iodide SIMS, and this is it being dropped by carefully and gently lowered by the gantry crane into position at CERN. Actually last fall. I noticed when I was looking at this that all those green straps are wrapped around the cage and they're not going underneath it. They didn't drop it, but I'm going to suggest a different way of doing that next time. Unless they really screwed those screws on very, very tightly. In any event, we made it. And first I'm going to talk about ammonium nitrate, so the nitric acid side. And those of you who are in the aerosol world are used to thinking of ammonium nitrate as a semi-volatile. That's how it's treated in essentially all models because it's way more volatile than ammonium sulfate and in general is semi-volatile. So that all the treatment of ammonium nitrate in the condensed phase is based on thermodynamic models like isorrhapia that give you the equilibrium vapor pressure of different inorganic constituents, and then you simply do an equilibrium calculation. And that's kind of almost first-year graduate student Seinfeld and Panda stuff. It's not always true, but this what I'm going to show you is an experiment from Cloud where Ming-Yi and others had nitric acid, sulfuric acid, and ammonia in the Cloud chamber, and that's shown here as a time series with a very large range on the log axis in the mixing ratios. These are measured, and what you see is nitric acid and ammonia up in the range of about a part per billion, of 1,000 parts per trillion there, and then at the time of the horizontal time zero, where you see the vertical dashed line, we formed sulfuric acid by oxidizing SO2. And you see the sulfuric acid concentration rising to a part per trillion or so. And that's typical of conditions. It's typical of urban conditions you might find in Beijing. And that's what we were working to study here. But the point is there's way more ammonia and nitric acid than there is sulfuric acid. And we're doing this at 5 degrees C in this case. So when we did that, this is a size distribution and a volume distribution of the particles. With the colors being proportional, the hotter colors, the warmer colors show higher volume or number, going from a couple of nanometers up to about 400 nanometers on each y-axis, and over the course of about an hour. Okay? And so what you see is the formation of particles very rapidly, and this is nucleation indeed by ammonium sulfate. Actually, it's ammonium bisulfate, but ammonia and sulfuric acid. And then after about 10 minutes, an extra mode shows up and grows very, very, very rapidly to much larger sizes, around 100 nanometers, at a rate that cannot possibly be explained by that 1 part per trillion of sulfuric acid. So the only thing in this experiment that has a big enough concentration to be the bug on that windshield is the nitric acid and the ammonia. And we don't think it's a liquid ammonia droplet. We know it isn't. And in fact, when we do the temperature programmed desorption, when Ming-Yi does, in the Figaro instrument, this is what's shown. The concentration of nitric acid on the left is 100,000 counts. The concentration of sulfate on the right is 5 counts. But it takes much warmer. You have to get much hotter, up to about 130 degrees, 120 degrees, to get the ammonium sulfate to evaporate. The ammonium nitrate is easy to drive off, so that's a semi-volatile part, essentially. Much lower temperature, it comes off. So these particles are almost pure ammonium nitrate with a little bit of sulfate as sort of a core. So that's what was driving the particle formation there. And we found, by repeating these experiments, 2 things. We did experiments at 5 degrees C, which are shown in purple here, and then cooled it down by 15 degrees to -10. Those results are shown in green. And what we have here is on the x-axis is the product of the nitric acid and the ammonia. And then the y-axis in this figure is the activation diameter. So it's the point where the growth went from sort of languid and slow to extremely rapid, this sort of explosive growth. And that activation diameter gets smaller as you move to the right. So the more you're driving on it, the more the excess saturation, as I'll show you, is, the smaller you activate. And the colder you are, dropping by 15 degrees basically decreases the whole thing by about an order of magnitude. So it's even easier as it gets colder. That's the bottom line there. And so this is the activation. This is the diameter where that extremely rapid explosive growth starts. And then this is actually the growth rate, again as a function of the product of ammonia and nitric acid, and again at +5 in purple and -10 in green. And once again, the growth rates correlate with that product. At lower temperature, for an equivalent product of concentrations, you get a much faster growth rate. And we can get very, very, very rapid growth, up to 1,000 nanometers an hour. Alternately, that means that if we only wait for 1/100th of an hour, right? So 30 seconds, we're going to go through 10 nanometers, and that actually gets the particles up past the size where they're those incredibly vulnerable small fry that are very twitchy and very diffusive and are lost with especially high probability. And so with a very little bit of this nudge of growth, particles can become big enough to be at least slightly less likely to be lost to larger particles. And we think that's interesting. So let's look at that in terms of a phase space. And so this is a phase space now with the nitric acid concentration on the x-axis in parts per trillion, and the ammonia concentration on the y-axis, again in parts per trillion. We've got a few orders of magnitude in each case, and we're actually mostly focused in on the kind of part per billion range, so you might see 10 to the 3 in the middle there. And just to give you a sense, the dashed diagonal is the 1-to-1 line. So things in the upper left have excess ammonia. And again, if you were in the New Fellows meeting, you might have heard Tong Zhu talking about the worry about decreasing ammonia too much and getting into conditions where you have potential acid rain. in many areas in eastern China, at least, it looks like there is, in fact, excess ammonia at the moment, which is why the interest in potentially regulating that as well. But this is a sort of a typical range. And we care about saturation ratios. So these diagonals show the saturation behavior of ammonium nitrate. And so the solid diagonal purple is saturation of 1. Right? So at those concentrations, at 10 degrees plus 5, degrees C, the system would be in equilibrium. And then the dashed are a factor of 5 and a factor of 25 for the dotted diagonals. So under those conditions, there's a huge supersaturation in the gas phase, or getting to be huge, and the system simply wants to drive growth, and it doesn't really care about the particles in any significant way other than what their diameter is. And so now we'll plot what we observed there with the activation diameters as the numbers inside those purple symbols. And the smaller the higher the saturation ratio, the smaller the activation diameter, as I showed you in the simple correlation plot there. And there's one case is that open symbol where we did not observe any activation, and that's below the saturation line, because we weren't under conditions where we could drive that concentration. So then if you cool down, the thing about getting cold, so under the same conditions, if we had the same production rate of nitric acid, the same emission rate of ammonia, we have the same sources for the gas phase, and we just make it colder. We have the same surface area of particles. Nothing about the gas phase concentrations is necessarily going to change, but we will change the thermodynamics. And so that same 3 set of saturated plus a factor of 5, a factor of 25 are now the green diagonals, and they've shifted a long way, 2 orders of magnitude to the left, factor of 30 to the left. And so under the similar conditions, we ran the experiment under slightly different conditions that are actually pretty representative of conditions often found in Beijing. Now at minus 10 degrees, the system is always heavily supersaturated. We see very small activation diameters and very rapid growth. So under these conditions, the ammonium nitrate really isn't semi-volatile, because the semi-volatile means I care about that gas phase activity. And the gas phase activity when I'm at a saturation ratio of 25, that makes it 24, right? I don't care about that difference. And so these particles are going to grow regardless, except when they're really, really small, and that Kelvin term actually makes the effective activity high enough so that you don't classically nucleate. But you'll grow on almost anything. Well, I can get colder still, and I can change the equation more, and Ming-Yi can make, and all the cloud students can make nucleation. And so these are experiments now just a little bit colder, and it's actually from right to left. It was an experiment where the chamber was being cooled progressively from minus 15 degrees to about minus 25 degrees, showing just nitric acid and ammonia on the top, in this case with some excess ammonia. And then the observed new particle formation rate. There's no sulfuric acid in this case, as measured. There's nothing in the particles that are forming, no sulfuric acid. We're nucleating particles as ammonium nitrate. The nucleation rate, as you'll see, isn't all that high. It's between 10 to the minus 2 and 10 to the minus 1 per cubic centimeter per second. But we only get down to minus 25 degrees C, and you see there's a very strong temperature dependence to that. So we'll kind of leave that as a tantalizing tidbit, and we'll report back on that at some point in the future. So now let's turn to the second favorite reaction and think about organics. Checking on the time. So now I've got condensation of multiple things. The organic chemistry is very complicated. We produce lots and lots and lots of molecules from these oxidation processes. And they're getting more and more interesting, as I'll discuss in a little bit. And the question is how to represent this complexity, where I have a huge number of individual species, each of them being formed in the gas phase at some saturation ratio, and they're going to have a different mole fraction because it's a complicated organic complex mixture in the particle phase that I care about, represented by these different colors. And the scheme that we've developed to represent that is indeed this thing we call the volatility basis set. So I'll walk you through this in a little bit, but it's sort of a blank slate on which to think about this complicated chemistry. We can represent things that we know with enormous accuracy and precision if we do, and we can also represent sort of stuff if we don't know about it. But we do, the sort of founding idea is that we want to keep track of all this stuff, whether we know what exactly it is or not, or whether we know exactly what chemistry it's going to do or not, because it's there, and we better pay attention to it. And so it gives us some flexibility to represent things that we understand well, or things that we don't necessarily understand all that well. And the thing we really care about here is vapor pressure, as I hope or volatility, saturation, concentration. And so the x-axis is exactly that, saturation, concentration. That's the thing I care about most. That's how I'm going to represent material in this space. And it's a pretty wide range, from 10 to the minus 5 micrograms per cubic meter on the left up to 10 to the 9 on the right. We don't actually worry about stuff over there in the volatile organic range on the right, but we put it there for completeness as the thought experiment. And you see these different colored stripes. Those are classes that we'll talk about. And the y-axis in this case is not all that important yet, so let's not worry about it. Let's get rid of it. And the different colored stripes are classes whose behavior I care about and can think about qualitatively. And we'll start on the left with what we call the extremely low volatility organics, the ELVOCs. And these are things that are really defined by saturation ratio. And this is really important. And it takes some, I don't actually care about vapor pressure per se. I care about saturation ratio driving growth. And so it's the saturation ratio that defines the qualitative behavior. Do I come back in a significant way once I hit a particle? And the ELVOCs don't. So they have saturation ratios of 100 or larger, and their tendency to drive growth is if a particle exists, if they hit a surface, they're pretty much going to stick, and the evaporation rate is trivial. The next class we call low volatility organics, or LVOCs, and these are things that have a saturation ratio significantly greater than 1. And so once again, if they hit a kind of a flat surface, they're done. They're going to condense. But because of that Kelvin curvature effect, I do care about evaporation for the smallest particles. So they actually don't stick to the tiny particles. Also, they can get a little bit of stuff in the gas phase and do very efficient gas phase chemistry, and that can do interesting stuff. But we're not going to talk about that here. So there are things where the vapor pressure matters, but in a kind of a subtle way. And then we get to the green bar, and these are semi-volatile organics, because they have saturation ratios near 1, or between 0.1 and 1, or something like that. And so they can be in equilibrium between the gas phase and the condensed phase quite easily. They also can't really drive growth, because if my saturation ratio is 0.1, then I'm going to be 10% in the condensed phase max, and so I'm going to kind of augment any growth I get by adding 10% to that growth. But they don't really drive it. They just kind of contribute to the best of their abilities. I also want to emphasize these things have amazingly low vapor pressures, right? These are things that have vapor pressures of 10 to the minus 10 atmospheres. So semi-volatile is in the eye of the beholder. If you put, I have a piece of wax that I should have brought here that I use for a demonstration. It's some paraffin. It's C25 pentacosane. And it's got a saturation ratio right smack in the middle of this range. And it's been on my desk for 20 years. And it's not gone anywhere. So it's not semi-volatile in a way that you would think about. But for the atmosphere, it actually matters. And that stuff does get in the gas phase. Given enough surface area and dilute enough conditions, it does evaporate. And that's all we're going to care about here. So the other ranges are kind of out of this story. So now let's think about the gas phase chemistry, that production side. But now not just OH plus NO2 makes nitric acid. That was kind of simple. Now let's do the gas phase organic chemistry. And this, we kind of understand, or understood maybe, in the bulk, in the mass of things that control ozone and whatnot. Roger Atkinson, Janet Airy, Paul Zeman have written hundreds and hundreds of really outstanding papers describing in detail the molecular oxidation of organic compounds. It's complicated, but we start on the top with an organic, we oxidize it, and we get a peroxy radical. Remember my favorite potential energy surface? All the rest I don't care about too much here, because the peroxy radical is the thing that has choices, and those choices can be to make a nitrate, to make a hydroperoxide, or do something else. And the kind of new kid on the block here is that the peroxy radicals turn out to be able to isomerize and stay as a peroxy radical, but add functionality and drive their vapor pressure downward. And that's interesting. And a great deal of work has been done recently on that chemistry, because that can generate very low vapor pressures very quickly in the gas phase. And the really new kid on the block is a little spin-forbidden process that turns out to be super efficient for interesting reasons. There's a super paper from Theo Korten's group describing the quantum chemistry of this. But these guys can bump into each other and make peroxides of twice the mass, ROOR, or C20s for the C10 hydrocarbons, for the alpha pinene and things. And so that's actually the newest chemistry, and those two things will feature in the last few slides here. So we can represent this in the two-dimensional volatility basis set, where that sequence of dots are those peroxy radicals that do auto-oxidation chemistry but remain peroxy radicals. And as they do so, the vapor pressure goes down and down and down and down. And I care about the vapor pressure of these radicals, but eventually they resolve and they turn into products that can have high concentrations and condense. And those are summarized in those contours there in a paper by my student Meredith Shervish, which is just showing up in ACP. And some of those resolve right below that diagonal tongue of peroxy radicals, and some of them combine in this reaction to make C20 peroxides, and those we now call ultra-low volatility organics, and they have saturation ratios greater than 10 to the 4 or something like that, and they can actually nucleate. So they drive the pure organic nucleation that I was talking about. And so they're interesting, and we're pretty sure that the nucleation in this system is really driven by those C20s almost exclusively. So we can sum that up into a one-dimensional space, but we're a little short on time, so I won't talk about that in detail. Now let's just turn a little bit to what happens, because I think this is where the gas phase chemistry and the pre-industrial to present-day chemistry really gets super interesting. And let's think of what happens if we don't look at that pure system of alpha pinene, but let's add some isoprene in a little bit now. And isoprene is a 5-carbon hydrocarbon. And think about what happens when those C10 peroxy radicals interact with a C5. Instead of making a 20-carbon compound, you make a 15-carbon compound, still with an incredibly low vapor pressure. So let's look at what we call pure organic nucleation. And this figure shows the nucleation rate, a little bit like I showed with the nitric acid case earlier, as a function of the so-called HOMs, which are just all of the very oxidized molecules, highly oxygenated organic molecules that you can measure with a nitrate chemical ionization mass spectrometer. And we see from alpha pinene, under neutral conditions, nucleation rates ranging from 10 to the minus 1, 10.1 to 10 per cubic centimeter per second, and they correlate very well with the concentration of these highly oxidized compounds. If you turn on the charge, that enhances the nucleation rate by up to a factor of 100. And then it levels off at the ion pair formation rate of a few per cubic centimeter per second, as expected. Now, actually, we're fairly sure that I should divide that x-axis by a factor of 30 or 100 for just the concentration of those ultra-low volatility organics to actually get the HOMs that are participating in the nucleation. What happens if to this system, without changing anything else, we add isoprene? In this case, oxidized by ozone through ozonolysis. And this was done by Martin Heinrizi. And the consequence under neutral conditions is the J, the nucleation rate, drops by a factor of 10. That's a big deal. We have the same amount of oxidation of the alpha pinene going on and the oxidation of isoprene, and the nucleation rate drops by a factor of 10. This is not OH suppression. We're forming C15 compounds instead of C20 compounds. And even though they have a very low vapor pressure, they're not ULVOCs, and they don't nucleate. Same thing happens for the charge condition. There's a very strong sensitivity to charge, but it's lower than it would be if it was just the alpha pinene system alone. So we believe is a compelling story of one of the ways that isoprene suppresses new particle formation. And we can look at growth as well. So let's look at the growth and wind up with that. I'm going to go past this and go to the isoprene growth. So now this is the formation rate that we observe at different sizes. as a function of how much the concentration of those highly oxidized, how high the home concentration is in the colors. So at high home, we see high formation rates, and the formation rates don't go down very fast as you get to larger particles because they're surviving. But then as you get to cooler colors, the formation rate, as you get bigger, as you go from 1.7 to 2.5 nanometers, the particles disappear because they got gobbled up. They didn't grow, they didn't survive. And again, if you add isoprene to that system, if you add isoprene to the system, we're adding more stuff that in theory could condense. It actually reduces the survival probability for the very smallest particles because once again, that critical step for the first few nanometers, these C15 compounds can't condense. But then eventually it settles down and they can condense on larger particles. So that's how gas phase chemistry influences the Charney report. I'll skip over those slides and simply say, another very interesting question to me is not just what did the pre-industrial atmosphere look like, but we often kind of implicitly assume as we go to a post-carbon environment, and we also try to reduce the mass concentration of the lethal fine particles, that we're just going to kind of walk back down the same path in this enormously complicated phase space that is the response of aerosols to anthropogenic forcing. That might be true, but it might also be true that we go a different way. And that question going forward of how aerosols respond to changes in anthropogenic emissions is, I think, just as interesting and compelling as the question of what the pre-industrial looked like compared to the present day. So with that, thank you very much for your attention.
Thank you, Neil, and we have time for questions. Once again, it's a very, very large room. It's hard to hear people in the back, so if you could come forward and use your outdoor voice to ask your questions. So with that, please, any questions? Come on, Andy.
Okay, Neil, can you be more specific about what alternative paths we might be walking backward?
Repeat the question.
Yes. So Andy asked if I could be more specific about what alternative paths. No. Next question. I mean, it really is speculation, but simply first of all, we don't, the health effects of ultrafines are an interesting question, as they might be different from the health effects of PM mass. But most of what we understand about dosage of toxicants from air pollution is that it's a mass-based dose response. But ultrafines are known, they have a better penetration to the deep lung because they have the same reason they die in the atmosphere. And so that's an interesting question that we don't really understand. But just simply that the balance between the oxidation rate and formation rate of condensable species in a post-carbon economy is still going to have some sources of pollution. It's kind of a lot less, but it's just not a pre-industrial economy. And so all I'm saying is that how we head back down to sort of a lower emission economy is not a one-dimensional space, and it's not guaranteed to be the same. But I haven't thought much about what I think is likely to happen. I'm implying that it might also be a policy relevant variable. So Jim asked if we see a difference in the physics in the condensation growth rate and nucleation rate, depending on whether we are ammonia limited or nitric acid limited. I didn't point it out, but the warmer experiments got very close to the 1-to-1 line. The short answer is no. That's my answer. Ask me a yes/no question, I guess I'm going to say no. But at first we thought we did. And we were a little puzzled by that because thermodynamically it sort of shouldn't matter. If it is ammonium nitrate, it actually is, you know, Le Chatelier and all that stuff. It shouldn't matter all that much. But that was actually before we started looking at the product. And we were looking at sort of just the nitric acid concentration, and there were these anomalies. And Rick Flagan essentially said, well, look at the product. And that settled into line nicely. So the physics of the response seemed to be just dependent on that saturation ratio and the product of the two.
Steve?
You're asking your title, what does this organic chemistry have to do with the Charney report? Your answer was nothing. But I think it has a lot to do with the Charney report in the sense of trying to infer what we call the climate sensitivity from observed temperature record and forcing. And this has a lot to do with forcing, and I know you recognize that, so maybe you could elaborate on that so that we don't end up thinking that the answer is nothing.
Fair enough. So Steve was chiding me for, again, saying no, but in the form of nothing to the question posed by my original. The Charney report, the preface also says a wait-and-see approach might mean waiting until it's too late, by the way. So indeed, the efforts to empirically infer climate sensitivity based on, so you know, if you know the forcing and you know the temperature change, you know at least the transient climate sensitivity, right? And there's a large amount of scholarship based on that. And I definitely alluded to that in the introductory material because I showed you how high gain the public sphere is to very small changes. If you appear to say, you know, so when you kind of follow through the logic of the introductory work from GLOMAP, saying that if we add in this source of pre-industrial aerosol, the inferred climate forcing from aerosols in GLOMAP went down some, which means that the overall forcing was slightly higher. So a higher forcing for the given period up to now means a lower sensitivity by a little tiny bit, right? And then MAGA got going, and well, then that happened. So yes, it's very important in our ability to match experiment and observations, for sure. And it also matters, I'm arguing, in the future to how we attempt to roll off the surface. So yes, I definitely think that aerosols matter to climate, and they're a huge part of understanding the sensitivity of climate to forcing and understanding forcing. And basically, clouds are everything, right? It's that condensed phase. We understand everything else about the climate system extraordinarily well, I would argue. You might disagree. But you get into the condensed phase, and that's where, you know, we can do mass balances and energy balances. Number balances, nobody, you know, you don't sit down in first-year physics and someone tells you about a number balance. They aren't there. And so that's the enormous freedom in the system that really makes it hard. That was more than no.
Okay, if there are no more questions, we'll bring the session to a close. Once again, I want to thank Neil for a terrific lecture here. But I also want to remind folks that the Turco lecture will be Thursday morning at 8 a.m. Sorry to get everybody out of bed early. And the topic will be, it's by Alexander Hall on why and how climate science must change. So Thursday morning, 8 o'clock, back in this room. So thank you, and let's give Neil another round of applause here.